which is a continuation of Chapter 4. Lectures 20 and 21 will cover the remainder of the material in Chapter 4, and then we will have a homework assignment over the entire chapter, which is going to be right here. There's no information under this right now, but that will be due if you're in this class in the fall of 18. It will be due on October 17th, or there will be a different day on your Moodle page if you're in a different semester, and then we'll have the midterm exam on that day. So we'll talk about all that. We'll do 2 more lectures on Chapter 4, and then on lecture number 22, we will have a review of the material up to this point in class. All right, so what is going on with this? See if I can get a better signal here. That looked really nasty, didn't it? Better. Okay. So here we go. The first thing that we talked about last time, I'm going to review this in just a split second. But we talked about pure bending, which we referred to as a situation where we had sigma but no tau. So in other words, we have only normal stress, no shearing stress. The more general case of bending involves both. But 2 examples that I gave you were if you were, for example, lifting free weights and the person lifting gripped the bar right here, the bar would be bent in a shape that would look like an arc of a circle, and there would be some center of curvature that could describe or subtend this arc. Another example would be if you had some sort of a prismatic structural member with rigid end caps and you placed C-clamps on the end caps and then bent them up or down, so that once again you would have a shape like this and some sort of a center of curvature that would subtend the arc. So when we have a shape like this, the axis will look like this. In this case, where the top of the axis elongates, this would be in tension. The bottom would be in compression here. The opposite is true. In other words, we stretch here, that's tension, compress here, or shorten here, that's compression, and the opposite is true here. While this happens if our cross-section had originally looked like a rectangle, this would get a little bit smaller, this would get a little bit bigger, and here it would be the opposite. This would get a little smaller, this would get a little bit bigger, so that this is the deformed cross-section, greatly exaggerated. This is the deformed cross-section, greatly exaggerated. Now, the other part is that if you look at the section, and you think about the bend, it will also subtend the arc of a circle, or concentric circles, really, if you consider all of the different layers. And we call this center C prime. And if this is the center of curvature, this is called the center of anti-clastic curvature.
I have a question.
Yep.
Why on their counterparts, like the deformed squares that you drew, why are they the surface area, the larger flat surface area pointing towards the center?
Well, it's because that's where the compression takes place. So if you think about Poisson's ratio, think about just stretching a prismatic member, okay? If it elongates on this axis, it's going to contract on the other axis, isn't it? Okay? If it's a homogeneous material. So it's the same thing here. If it expands here, it contracts on the axis. If it contracts here, it expands on the axis. So, and we're talking about homogeneous materials, but that's it's just, it has to do with, and it's related by Poisson's ratio here, just as it was with an axial load on a prismatic member. Good question. And if you remember, Poisson's ratio is designated with the Greek letter nu. All right. Well, it turns out that the relationship is that if this radius is referred to as rho, remember this is referred to as rho prime, and this is called the radius of curvature. And although P prime is often called the radius of anticlastic curvature, the term we use, for reasons it's just a standard, it's a convention, is 1 over rho prime, which is not called the radius of anticlastic curvature, which is just called anticlastic curvature. So in other words, here we have units of, or dimensions of length. Here we have dimensions of length to the -1. But it turns out that anticlastic curvature for a prismatic member in pure bending is equal to Poisson's ratio divided by the radius of anticlastic curvature on the axis. So once again, nu, or Poisson's ratio, relates what's happening on the axis to what's happening on the cross-section. So, and that value varies from material to material. So, having said that, that kind of breaks up the geometry. A couple of other points I just want to reiterate really quickly, and these are, I talk about these extensively on lecture 19 on the video. But somewhere in the middle, if this shortens and this elongates, if this elongates and this shortens, somewhere in the middle is a place where the length remains unchanged, and that is referred to as the neutral axis. And it also turns out that at the neutral axis, the stress is equal to 0. In other words, the stress is in tension here, positive. The stress is negative in compression here, and somewhere, not necessarily in the geometric middle, but somewhere, which we'll talk about in just a moment, there will be a place where there is no elongation or shortening, there is no tension or compression. And that location is referred to as the neutral axis. So this leads us to the idea of epsilon due to the unit of dimensional change due to pure bending. It will be a maximum value at the top if we're in tension here. It will be a minimum value at the bottom, which will be compression, and it will be 0 at the neutral axis. And the relationship for a homogeneous non-composite material is linear across the section. Okay, so you can determine what the stretch would be anywhere if you knew the location of the neutral axis and the maximum tension or compression. Okay, so then I introduced, pretty much without proof, some formulas which are called the elastic flexure formulas. And they tell us that for pure bending, that sigma at any point on this axis is equal to the moment applied, this is the max, times c, which is the distance from the neutral axis to the surface, over I, which is called the moment of inertia, which we're going to break down in just a moment. And that sigma at any point on this curve is equal to minus my, in other words, the distance, whatever it is, not necessarily the maximum distance, but the distance above or below over the moment of inertia. So that tells us that not only is epsilon linearly proportional and 0 at the neutral axis, sigma is also linearly proportional and 0 at the neutral axis. Okay, so this is the geometric representation of the state of stress and the deformation of the section. Well, what is I? I is called the moment of inertia, which I always abbreviate this way because moment of inertia is very difficult to write out over and over again. And what we can think about it in this class basically is a resistance to bending based on the size and shape of a structural member. So an example that I used on 19 is like this ruler. If I bend it in this direction, it bends quite easily, and yet without changing the mass or the size, bending it in the other direction is more difficult. That is an indication that the moment of inertia in this plane is quite a bit smaller than the moment of inertia in this plane. So when I is greater, let's say, when I increases, resistance to bending increases. Okay. Now, the thing about I is that it involves not only the size but the shape of an object. So one common design element is an I-beam. And the reason for that is, why do we have this instead of something that looks like this for a structural member? Well, the reason is that the flanges of this I-beam, for reasons that you'll understand in just a moment, contribute significantly to a high moment of inertia without all of the mass. So in other words, you lose the mass of this part of the web, and so this is lighter, but it has nearly the same moment of inertia as this. Okay, so it resists bending very well for a lightweight shape. Also, these are very standardized shapes, and the moments of inertia for all kinds of different I-beams are tabulated in the back of your textbook. And if you look here, for example, in Appendix C, you'll see the properties of rolled steel shapes in U.S. customary units. They show you an I-beam, and they give you the moment of inertia in the X direction, the moment of inertia in the Y direction. So that depends on if you're trying to bend it this way, about the X-axis, or folding it into itself, about the Y-axis. So you can see that the moment of inertia here about the X-axis is very, very large compared to the Y-axis. So in other words, when you build something with an I-beam, like a bridge, let's just say that the sides, here you have a bridge like this, and you want the sides of the bridge to be like this, because the bridge wants to bend in this direction. When you load it, it actually bends like this, I guess, would be the best way to put it. Flexes in this way. So you need to have that resistance to bending in this direction. If you laid the I-beams like this, that would be a terrible use of an I-beam. That would not resist bending in the same way. Yes?
The stiffness of the I-beam is even better than the raw material.
Isn't that amazing? Because it's not weighing itself down. Yeah, and when they roll the shape, they can do some structural things with it. But they're wonderful. They're a wonderful design element. I agree with you. So yeah, the stiffness, which is another good indication, that's another good descriptor for what moment of inertia does for us. You know, is definitely a much better much better for this shape. Now, so the other part of this is, if you look at this, if I is a geometric property, C over I is also a geometric property, and sometimes we call this S, not for stiffness, but for section modulus. So I is equal to moment of inertia. C over I is equal to S, which is called the section modulus. And it's just because it makes, you just have to do one less calculation if you work with a section modulus. And for a given shape, the section modulus will be the same. Okay, so now we have some equations, and we have some ideas about this idea of bending. The one thing I want to iterate, I want to be really clear about, moment of inertia is a very complicated mathematical concept, and it means a whole bunch of different things. For example, in addition to being a resistance to bending, it's also a resistance to spinning. So if you have like a ruler and you take the axis right here, you have a certain resistance to spinning. here the resistance is different, isn't it? So in other words, you have to make it spin differently on this axis than you do on this axis, even though you haven't changed anything about the orientation or the shape or the size of the ruler. So moment of inertia is not, what we're going to talk about in this place, in this chapter, is the moment of inertia about the centroid of an object, which is also the neutral axis. You may remember the idea of centroid from statics. If not, here we can use it functionally similar to neutral axis. It's a bigger concept, but it works the same way for us here. So what we're talking about is a very broad mathematical concept. So when I say in here that it's a resistance to bending, that's true. It's also a lot of other things. So just so that you know, if it gets introduced later on, well, it will get introduced later on, you'll see that it can describe a lot of other physical properties as well. All right, so let's talk about the moment of inertia. How do you find I? Well, you can calculate it, or you can look it up in a table. And I've shown you one of the tables. If you have a general shape, there are several tabulated moments of inertia in the outside back cover of your book. And you'll notice that they are described differently. We have Ix prime, Iy prime, with a little bar above them, Ix, Iy, and then we have J sub c, which we actually talked about in torsion, where we talked about the polar moment of inertia. All right, we look at this nomenclature. I bar means about the centroid, which for our purposes is about the neutral axis. And for non-composite shapes, this is the one that we're going to be using. I sub x bar, when they tabulate this, what they're saying is about the x-axis. And generally speaking, this is what we'll be using. Now, your authors in this textbook put an Ix prime because if you look at the axes they use, they call this the x-axis, and they call the centroidal axis the x prime axis. So they're just making a clear distinction. Ix is about the x-axis, whereas Ix prime is about the x prime axis. And when they put a dash above it, that's saying it's centroidal. So they're just double confirming that this is the moment of inertia about the neutral axis, or the centroidal axis, to speak more generally. Okay, so those are the two places that you're going to be able to find x bar. They tend to form, I's tend to have, there are two different kinds. There are mass moments of inertia and areal moments of inertia. And we're going to be talking about areal moments of inertia in this section, and they have dimensions of length to the fourth. Inches to the fourth, feet to the fourth, meters to the fourth, centimeters to the fourth, and so forth. Ha ha. So anyway, so we have sigma, if it's equal to n minus my over I, we know that a moment has dimensions of force times distance, or length. We know that y has dimensions of length. We know that moment of inertia has dimensions of length to the fourth. So we have length squared on top, canceling to length squared down here. So we have dimensions of force per length squared, which is the proper dimension for sigma, or for stress of any sort. All right, now we learned to calculate moments when we were doing the method of sections earlier in our discussion. So if you're not given a moment, you need to compute a moment. The moment is equal to a force times the distance, or in the case of a moment of a couple, it's equal to the parallel force times the distance between them. So for example, if you have a weightlifter, once again, and the weights are pulling down with, let's say, 100 pounds, and the weightlifter's hands are pushing up with a force of 100 pounds. If it's not, something's going to give, right? The weight's going to rotate out of his or her hands, or it's going to fall to the ground, or some sort of thing. So it has to be like that. If this distance is, say, 7 inches, let's just say 1 foot, just for kicks. This force system is a couple, spinning it this way. This force system is a couple spinning it this way, counteracting it, and the moment of the couple is equal to the force times the distance between the two equal and opposite forces. So this would be 100 pounds times 1 foot, or 100 foot-pounds. Okay. Alrighty, so let's take a look at a problem and how we view it. I'm going to go ahead and do problem number 1, 4.1, and I think I'll do 4.2 as well if I have time. But let me start with 4.1, because we have to, this is, once again, it's not a deceptively easy equation, but it's one where we have to consider all of the factors. Okay, 4.1 says, knowing that the couple shown acts in a vertical plane, determine the stress at point A and the stress at point B. And we are drawing a cross-section that is a hollowed out rectangle. And we're given dimensions in millimeters. We're told that from here to here is 20 millimeters, from here to here is 40 millimeters, and 20 here, so we have lots of symmetry. On these types of problems, at this stage of the game, we have to have lots of symmetry, or we're not able to do the math, because moments of inertia are integrals. They're actually, the actual form of a moment of inertia is the integral of y squared dA, or on the other axis, x squared dA. And we're not going to deal with these integral forms. The most that we'll do is add things together to do a summation. But on something like this, we can compute it quite a bunch easier. Okay, so we're told here that the cross-section looks like this, and that basically this structural member is extruded from a wall. The moment is applied in this plane, and that moment has a magnitude of 15 kilonewton meters. Right? Now, if you look at the drawing, and I'm sure that everybody who's done drafting, I'm sure that Christian, that's probably like second nature to you, right? Hidden, this hollow part is hidden inside of the structure on that view. So they ask us, what is the stress at point A, which is right here, and I'm going to do A, and then I'm going to leave B to you. All right. So that will be the first part of your homework. Will be 4.1, number B, or letter B. All right. So let's think about this. How am I going to find the stress at A? Well, this is pure bending, so it's equal to minus my over I. I know that my moment is 15 kilonewton meters. What is my y? My distance from my neutral axis. Okay, because this is symmetric, the neutral axis is going to go right through the middle. Okay, and everything that we deal with at first is going to be symmetric. So we're basically going to be able to fold it and find the distances and the location of the neutral axis just from being able to fold something together. If you're dealing with something that is non-symmetric, you have to go a little bit farther in your analysis to find out where that is. But for now, we're going to leave it at that. Okay, so if this is 80 and 20 and 20, the distance from my neutral axis, which is the y that I'm talking about because the stress at the neutral axis is equal to 0, my distance is from here to here, which is going to be 40 millimeters, which is 40 times 10 to the negative third meters. Okay? Now what about my moment of inertia? That is the harder one. Well, the answer is, if you look at this, the hollowed out rectangle in the middle and the solid rectangle outside have the same neutral axis, which is right in the middle here. And because they have the same neutral axis, all I have to do is to find the moment of inertia of the outside rectangle and subtract the moment of inertia of the inside rectangle. So to do that, I go to the back of the book and I look at this and I see that my IX bar is 1/12 times the base times the height to the third power. I have a rectangle is 1/12 times the base times the height to the third power. All right, so in my case, the eye of this hollowed out rectangle is going to be 1/12 times the parentheses base height to the third of the outside minus base height to the third of the inside. All right, now you can keep this in millimeters if you want, but if you do, you're going to have to remember that when you have millimeters at the end, you're going to have to go, there's 1,000 millimeters per meter, and you're going to have to do that to the fourth power. So yeah, you can do it either way, but I kind of recommend changing everything into meters at this point.
So should we, when we're starting this, should we just convert everything to units we need to be?
I would, and Emma had asked that question, and it's an excellent question, because the answer is you do not have to, but just I find it easier to not drop a power of 10 doing it. So I routinely do it. If you're comfortable with it, doing it the other way, that's absolutely fine. But I do it this way because I find that more students are able to keep their powers of 10 straight doing it by converting to meters or to base units right away. All right, so my I then is equal to 1/12, right? I just factored the 1/12 out, times the outside, which my base is 40 plus 20 plus 20, which is 80, which is times 10 to the negative third, times the height of the outside, which is 80 plus 40, which is 120, times 10 to the minus third. That height is raised to the third power. And I subtract from that the inside base, which is 40, times 10 to the minus third, times the height of the inside rectangle, which is 80, times 10 to the minus third, and that raised to the third power. And this is going to be meters, meters to the third, minus meters, meters to the third. So that answer will be meters to the fourth, won't it? All right, so my I then is equal to 1/12. Now if I do my math here, did I bring my calculator? Yes, I did. All right. So I have, I'm going to start here, 120 raised to the third power times 80. Okay, and then this, if you look at your powers of 10, this is going to be 10 to the 9th. So this is 10 to the minus 12th. So let's see. So that's this itty bitty number, or I could just say 1.3824 times 10 to the minus 4. And then the bottom number here is 80, also raised to the third power, multiplied by 40. And then that is also 9, 10, 11, 12. Which is 2.048 times 10 to the minus 5 meters to the fourth. So if I take this number and I subtract it from this, oh shoot, don't do that. So I have 1.3824, where's my E button, 10, oh, wrong one, 1.3824, second function E to the negative 4, and subtract from that 2.048, and the power here is the minus fifth. That number becomes this little bitty number, which is 0.000117776. So I divide that number by 12, and I get my I is equal to 9.813 times 10 to the 6 minus 6 meters to the fourth. Okay, so there's my I. Now, when you do part B, the I will remain unchanged, so you can use this work to that point. All right. So continuing on, now I know, so therefore, my sigma at point A is equal to negative 15 kilonewton meters times my y, which is, I am above the neutral axis, so it's positive, 40 times 10 to the minus 3 meters, divided by my moment of inertia, which is 9.813 times 10 to the negative 6 meters to the fourth. Once again, checking my units, I have kilonewtons per meter squared, which is kPa, and this is a negative, which we'll talk about in just a second. My sigma at A then is equal to, the numeric value is, okay, this number 1 over that number times 15 times 40 times 10 to the negative third. And so my number is minus 61141 kPa, or I could say minus 61.1 MPa. Right? All right, why is this value negative? Look at this picture and tell me why. Sorry?
Is it going against the moment?
Right, exactly. If you think about it, the moment is bending it up. So is this is above the neutral axis in tension or in compression? Yep, which is negative, right? So the sign convention still works. All right. So do you guys have any questions at this point? All right, what I'd like you to do, because we only have 8 minutes left, for your homework, I want you to do 4.1b, and then I also want you to take a look at problem 4.2. And I'm going to give you a little lead-in on this, and you'll be finding the stress at 2 different points. When you find the moment of inertia of this shape, all right, there's a couple of different ways to do it. But what I would do is break it down into 2 times the little arm, okay? And that would be 2 times 1/12 base height to the third of the little arm, this and this. And add to that the larger rectangle, 1/12 times the base times the height to the third of that. The reason being that each of these, if you look at it that way, has the same neutral axis. If you break it down into this plus this and this, these do not all have the same neutral axis, so the work will become more complicated. You may remember, if you've had statics, there is an axiom called the parallel axis theorem, and the parallel axis theorem would allow you to find the moment of inertia using this. However, it's impractical when you can just do it like this, since you have the same neutral axis. The other thing you could do is look at it as a rectangle and then subtract off 4 of these little rectangles. But once again, these 4 little rectangles do not have the same neutral axis. So the best method of attack is to do this, because everything has the same neutral axis, so you can just arithmetically add them together. All right? So you start with a good picture, and you move forward. So your homework for tonight will be, or actually you're finishing up chapter 3, but your homework for tomorrow night will be 4.1 part B and 4.2 parts A and B. And then we'll continue talking about this on Friday. All right? Yes, sir?
So we have a midterm.
Yes.
And when is the homework due?
Wednesday. Why is that? Yeah, you need to have it done to do the midterm. So yeah, that's kind of the deal. So, and then that will also allow you, after you do your homework, to go through and develop a good formula sheet so that you'll have your material ready for the exam. All right. All right. Well, I'm going to stop streaming at this point. So that's the end of the information for today. There we go.